Insertion sort is a sort in which there is a fundamental rule. If the number on the left hand side is less than the number on the right hand side, then we continue, and this is the case for ascending order. And likewise, if the number on the left hand side of the array is greater than the number on the right hand side of the array, we do a swap. Now let's have a look at how exactly this works. We have the following elements: 2, 3, 2, 5, 4, 7 and 0. We have two pointers. The first points to 3, the second points to 2. Is 3 less than 2? The outcome is false, and that's why we swapped 3 and 2 to correct the locations with respect to each other. So 2 and 3 get corrected with respect to each other, and after the swap they are in the right locations. Similarly, we compare 3 and 5. 3 is less than 5, the condition is true, and we just continue, which means both the pointers move by a position of 1. They now point to 5 and 4 respectively. Is 5 less than 4? The answer is false, because 5 is indeed greater than 4, and we swap 5 and 4. And then we have the next set where 4 and 5 are in the correct location with respect to each other. Also, please observe that at this point in time, 4 is also correctly placed with respect to all its neighbors on the left hand side, and to begin with, its immediate neighbor 3 is also correctly positioned with respect to the current location of 4. Hence, no readjustment is required on the left hand side. And likewise, when we compare 5 and 7, 5 is less than 7, we continue, and the pointers now point to 7 and 0, and no correction is needed at this point in time. However, when we compare 7 and 0, we realize that the condition is false, and then we swap 7 and 0. Once we swap 7 and 0, we now realize that the ordering is broken on the left hand side of 0, because the immediate neighbor of 0 is 5, and that is not relatively correctly placed for ascending order with respect to 0. Hence, we compare 5 and 0, the condition is false, and we do a swap of 5 and 0. So 0 is here, 5 is here now, and now again the same thing is done with respect to 4 and 0. We are now in fact moving from right to left, though we earlier started moving from left to right, and that's because when we moved left to right, we did a swap, and that swap violated a condition on the left hand side of the immediate neighbor, right? So as soon as the left hand side condition is violated, or the number after swap is not correctly positioned with respect to the number on the left hand side, as is the case over here, right, with respect to 4 and 0, we correct it with a swap. So 0 and 4, they once again swap places, and the same condition holds true. We again compare 0 and 3. 0 and 3 will interchange places, and the same holds true for 0 and 2. 0 and 2 again exchange places, and the array is now completely sorted. Now if we realize insertion sort, the worst case complexity is O of n square. That's because we in this case use two loops, one the inner loop where we move from left to right, and one is the outer loop where we again move from left to right. But in addition to the inner loop where we move from left to right, we also have an inner loop where we move from right to left, right? That's the reason why we have an outer loop, and we have one inner loop for the left to right traversal, and another inner loop for the right to left traversal, and hence the complexity in the worst case scenario is n square. Memory complexity is over 1, and it's a constant, and the usage criteria which is best suited for insertion sort is when the data is nearly sorted.